Have you ever tried to draw something that's, well, just impossible to capture in a single picture? That's the puzzle we're tackling today in chemistry. We're going to look at why sometimes one drawing just isn't enough to show what a molecule is really like.
All right, let's give this a shot. We're going to be molecular illustrators today. Our subject is benzene, C6H6. So that's 6 carbon atoms and 6 hydrogen atoms. Sounds simple enough to sketch out, doesn't it? Okay, so here's my first guess. We could draw it like this, a nice, neat little hexagon of carbons, and we'll just pop in some alternating double and single bonds. It works. Every carbon has 4 bonds, all the rules are followed, looks pretty solid.
But hang on a second. I could just as easily have drawn it like this, couldn't I? All I did was shift the double bonds over by one spot. It's totally valid too. So, which one is the real benzene? Something about this feels off, like neither picture is telling the whole story.
And here's the big secret. You're right to feel that way. The truth is, both of those drawings are wrong. Or, well, maybe it's better to say they're incomplete. They're just our best attempt to put a 3D quantum-level reality onto a 2D piece of paper. And that's the problem we're here to solve.
So how do we know our drawings are off? Well, this is where real-world evidence comes in and just blows our simple pictures out of the water. If our drawings were right, we'd expect to find 2 different bond lengths, right? A long one for the single bonds and a shorter one for the double bonds. But when we actually measure them, we find something amazing. Every single carbon-carbon bond in benzene is exactly the same length. It's 139 picometers, a perfect average right between a normal single and double bond.
Okay, so if the individual drawings can't be right, what does the real molecule actually look like? Well, to understand that, we have to move beyond these static, frozen pictures. We need to start thinking about the real molecule as a hybrid.
And that brings us to the most important idea of the day, the resonance hybrid. The real molecule isn't flipping between our drawings. It's actually a single, stable thing that's a weighted average of all the possible drawings we can make. Those drawings we made? They're called canonical forms, and they're just hypothetical tools for our brain. The hybrid is the real thing.
This quote really just nails it. Canonical forms are imaginary, while the hybrid represents the actual electronic state. Those drawings are just our mind's attempt to make sense of a quantum reality. In the actual molecule, those electrons aren't locked into one double bond or another. They're what we call delocalized, meaning they're smeared out and shared across the entire ring.
Now here's a great analogy to bust a really common misconception. People often think the molecule is rapidly flipping back and forth between the 2 structures we drew. It's not. Think about a mule. A mule is a hybrid of a horse and a donkey. It's not a horse for a second, then a donkey for a second. It is at all times 100% a mule. In the same way, benzene is at all times 100% the resonance hybrid.
But this electron roaming, this delocalization, doesn't just happen willy-nilly. Chemistry has rules, and there's a very strict set of conditions that have to be met for this thing we call resonance to even be possible.
So there are 3 main requirements. First, the atoms involved have to be lying flat in the same plane. This planarity is crucial so their electron orbitals can line up and overlap. Second, you need a conjugated system, which is just a fancy way of saying you need an unbroken chain of alternating double and single bonds. And third, and this one is a non-negotiable fundamental rule, only the more mobile pi electrons in the double bonds are allowed to move. The single bonds, the sigma bonds that form the molecule's skeleton, they are sacred. They never ever break during resonance.
Okay, now that we get the basic idea, let's see how different groups attached to a molecule can influence this flow of electrons. This is where we get into this cool idea of a molecular push and pull system, which has a technical name, the Mesomeric Effect. The Mesomeric Effect is really just a specific way to talk about resonance when you have a functional group attached to one of these conjugated systems. And it basically comes in 2 flavors. You can have a positive, or plus M effect. That's when a group donates or pushes electrons into the system. Or you can have a negative, or minus M effect, where a group withdraws or pulls electrons out of the system.
So who are these generous electron donors? Well, they're typically groups that have lone pairs of electrons just sitting there, ready to be shared. Think of the hydroxyl group on an alcohol, or an amino group. Even the halogens can act as plus M groups. They're all capable of pushing their electron density into the ring.
And what about the electron withdrawers?
These are the electron-greedy groups. They usually have double or triple bonds to a really electronegative atom that's just desperate for electrons. We're talking about groups like the nitro group, the cyano group, or the carbonyls you find in things like aldehydes and carboxylic acids. They actively suck electron density out of the system and towards themselves. Now this is where things get really interesting, because resonance isn't the only game in town. There's another electronic effect called the inductive effect, which is all about pulling electrons through the sturdy single bonds. So you often get this battle, this tug of war, inside a molecule for electronic control.
So that leads us to the big question, right? When you have these two forces opposing each other inside a molecule, which one is stronger? Who wins the fight? Which effect is going to dictate how the molecule behaves?
Well, there's a pretty clear general rule here. In most cases, resonance is the heavyweight champion. The ability to move entire pairs of electrons all around a conjugated system is just a much more powerful effect than the relatively weak tug of induction through single bonds. So most of the time, resonance wins. But, you knew there had to be a but, right? There's one very famous exception to this rule: the halogens. See, halogens are super electronegative, which means they have a very strong inductive electron withdrawing effect. It's actually so strong that it overpowers their ability to donate electrons through resonance. This leads to this fascinating split decision. Their powerful inductive effect makes the whole molecule less reactive, but their weaker resonance effect still wins the fight over where a reaction will happen, directing any newcomers to very specific positions on the ring.
Okay, so after all this theory, what's the real-world payoff? I mean, why does any of this matter? Why does the universe seem to favor molecules that can spread their electrons out like this? The answer is incredibly simple. It's all about stability.
Molecules that have resonance are way more stable than you'd ever predict just by looking at one of their drawings. We can actually measure this extra stability, and it's called resonance energy. For benzene, letting those electrons roam free makes the molecule a whopping 36 kilocalories per mole more stable than a hypothetical version where the bonds were frozen in place. That is a massive stability bonus.
And this one concept is just so powerful. It's like a key that unlocks countless chemical mysteries. It finally explains our original puzzle, why all the bonds in benzene are identical. It explains why a molecule like phenol is so much more acidic than ethanol. It's because the ion it forms is stabilized by resonance. And maybe most importantly, it allows us to predict with stunning accuracy how and where chemical reactions are going to happen.
So at the end of the day, we've seen that those simple lines we draw between atoms are just that, a simplification, a useful model. The reality is this much more dynamic, blended, beautiful hybrid. And that kind of leaves you with one final thought, doesn't it? If the very idea of a fixed, static chemical bond is just a convenient story we tell ourselves, what other rules of chemistry aren't nearly as rigid as they first appear?